External factors, meteors, very difficult to calculate when the next meteor might hit the planet, who knows. And high-level jet streams, that's also something that's very difficult to model. Or solar flares, who knows when the next solar flare will come from the sun. We have gamma rays that come from deep space, that's also something that's variable. So those rays come in, they heat the planet, but they're not predictable. And the oceanic currents. So if we look at oceans, that's one of our big drivers though. The oceans are what we call the flywheel of a climate. The oceanic current is actually what stabilizes our current climate and makes us have this relative temperature stability. With the top skin of the global ocean being able to store the same amount of heat as the entire atmosphere. So the top 50 meters of water has the same energy or heat holding capacity as the entire atmosphere. That's a big deal. So we can focus on the oceans again and see what's going on with our ocean. Is our ocean warming? Is our ocean cooling? And that's another way that they can try to get a good model or a trend about what's going to happen in the future. So the heat of the Earth is being stored in our oceans. So if we look at our oceans, what's happening? Well, 90% of the excess heat that was produced through industrialization in the last 50 years is said to have been stored in the ocean. So our oceans tend to suck up the heat that we produce in excess. This is not solar radiation, that's a reflected thing. This is us if I turn on an air conditioner, do you think it makes the world cooler or hotter? Hotter. So I might be cool, but that air conditioner makes heat to make cool. So we're like a weird thing. And then we burn fossil fuels to run the air conditioner, these type of things. So this heat is it's not really coming out of the planet. So that's what thing. So that is increasing the salinity of the oceans. As the salinity of the oceans are increasing, then the biology is getting changed, and then we're even having issues where that biology is releasing more carbon in carbon releases. So here's your currents all over the Earth, oceanic currents. And if we look at those specific, we have the El Niño effect and the La Niña effect. And these are also very interesting to see that these are shifting. They always have. We've had a lot in recent years, in the last 20 years, people putting a lot of emphasis on this. Oh, it's an El Niño. But they've actually always been there. So this is where we get a difference in cooling coming from basically pressure situations. So as the current or the belt shifts, it creates different pressures, and that moves the climate on these two things inversely. One hot, one cold, one hot, one cold. We have solar activity. So currently, solar radiations and the solar flares can be tracked. We can actually use computers now to do that. Before, they tracked it by hand. 1%, there's a change of solar activity of 1% change every 11 years. That's pretty accurate. And so the Earth's temperature can closely match solar activity for the last 1,150 years. So as they look at the solar flares and the temperature of the Earth, it's almost a direct overlay, going back 1,150 years with no change. It currently still tracks that, even with carbon. So that's another issue that solar flares are increasing also. So we're in an increased solar flare cycle at the same time. So cosmic ray particles are too small to form nuclei for clouds, and they're a limiting influence on our cloud formation, so that scientists will also study that. So that creates water vapor in the air, and the water vapor is the reflective surface, or what we see as greenhouse gas. So this doesn't really cause what we describe as global warming, though. Global warming is more about the aerosols, the pollutants, and the carbon, not water. So we don't see a reflectivity of heat caused by water. But we do have polar influences. So when we go to our poles, and as we can see now, our poles are starting to melt. So we're starting to lose ice cover. Ice is reflective. So when the radiation comes and hits the poles, the ice helps to reflect radiation. So guess what happens if you lose the ice? You absorb more heat. So that's a problem. So it can be exacerbated by the hotter it gets, the more we lose ice, and then the hotter it's going to get. Kind of strange. So the change in the Arctic sea ice, so they can do that. So 90% of our total ice is in the Arctic Sea. And we can look at how that has shifted and is starting to decline on a rapid rate. So this is what a modeling of the Arctic ice losses. So far, we've lost in the last, what you might say about 30 years, 8% of the ice in only 30 years. It's really fast. We saw our glaciers melting across the planet. We've lost 2% of the ice due to glacier melt. And this can cause climate chaos. We have droughts, fires, floods, storms, ocean rises, temperature extremes, or even cyclones and tornadoes. So if that chaos, and we start to look at how that's working, well, let's look back in the past again. We can go back to those ice core samples, and we can see times in the past when they had these fluctuations also. So at this particular time was called Lake Azazi. An ice dam broke 12,900 years ago, and it raised the sea levels 1 meter around the whole planet in 1 year. Boom. So the Gulf Stream shut down at that point, and that brought on, for 500 years, an ice age. Just from one event. Climate chaos. So our climate systems are complex and dynamic. That's the most thing to take out of this. And their small changes to forcing can trigger unpredictable results. So we don't know right now exactly what's going to happen if we're losing 30% and every day losing more ice. Exactly how fast can it go? Nobody really knows. Is it going to take another 1,000 years? Or is it going to take another 100 years? And this is a problem.